In this video, we're going to talk about different types of numbers. If you have to memorize the different types of numbers for a class, then this is a great place to start. If not, then we're going to get on the same page by just quickly reviewing these different types of numbers. So we start with the natural numbers, which are sometimes called the counting numbers, because we start at 1 and we just count up from there. 1, 2, 3, 4, 5, 6, so on and so on until we get to 100, a million, a trillion, and it just keeps going. If we want to add in 0, we can do that, and sometimes we write that little subscript of a 0. Sometimes we call these the whole numbers, the natural numbers with 0. That's not too important. Now, the integers have all the natural numbers, they have 0, and they have these negative numbers. So an example of an integer is something like -7. Now, -7 is an integer, but it's not a natural number, because there's no negatives in the natural numbers. On the other hand, something like 20 is both a natural number and an integer. We can clearly count up to 20 in the natural numbers, and if you look at the integers include all the natural numbers, 1, 2, 3, 4, 5, and so on. Now, what's an example of a number that's not an integer? Well, how about something like a fraction? Now, when we move to if we want to include all the fractions, then we move to the rational numbers. So, for instance, 1/2 is a rational number, but it's not an integer. Now, 1/2 is a rational number because if you look, 1 is an integer in the top and 2 is an integer in the bottom. So when we make a fraction with integers, that's a rational number. Now, can you think of any examples of a number that is both a rational number and an integer? Well, 5 is both. Why? Think about it. 5 is definitely an integer and a natural number for that matter, but it's also a fraction because 5 is the same thing as 5/1. Now, 5 is an integer and 1 is an integer, so we can write 5 as a fraction of integers. So 5 is a rational number and an integer. In fact, all the integers are rational numbers. Now, what about things that are not rational numbers? Well, the square root of 2 is not a rational number, but it is something called a real number. So real numbers are all the rational numbers, all the fractions, and there are these mysterious things like the square root of 2 and the square root of 3, and numbers that we call irrational. So, for example, 5/2 is a fraction, so it's both a real number and a rational number. But the square root of 2 is only a real number. We'll talk more about the real numbers at the end of the video, but they're really, really, really important. They're the numbers we'll be using most often in this course. Finally, we get to the complex numbers, which are just real numbers with imaginary numbers, things of the form a plus bi, where a and b are real and I is the imaginary number square root of -1. Now, if the complex numbers right now seem mysterious and weird to you, don't worry about it. We'll talk about it later. But let's revisit the real number line, or the real numbers. So this is the real number line, and it's just a continuous line of numbers. You can see we have all the integers, 1, 2, 3, and so on. We also have everything in between. So, for example, right where that green dot is, that's perhaps the square root of 2, because the square root of 2 is approximately 1.414, and it keeps going on forever. So it's just a little less than 1.5. Now, the interesting thing about this is that if we were to draw a number line with only rational numbers, so only fractions, well, we already talked about the fact that the square root of 2 is not a rational number. It's not a fraction. So if we drew a number line with only fractions, there would be holes in it. There would be a hole where the square root of 2 goes. So the real number line is really special. It has this property that every number is there. There's no holes or jumps or gaps. And we'll use the real number line in that sense, that basically when we can think of it as all the numbers on that line, the whole line is continuous and filled with numbers. Okay, see you in the next video. We have two groups of marbles on screen, 5 blue marbles and 2 red marbles. And if I asked you to tell me how many total marbles are there, some of you might write, well, there's 5 blue ones plus 2 red ones, so there's 7 marbles in total. But some of you might start counting with the red, and you'd say there's 2 red ones plus 5 blue ones, which still gives you a total of 7 marbles. So the important thing here is that 5 plus 2 is equal to 2 plus 5. It doesn't matter which order we add in, because we're counting the same number of marbles. And this is a really important property of addition. It's called the commutative property of addition. And it says that if we have any two numbers, a and b, then a plus b is equal to b plus a. So it doesn't matter which order we add two numbers in. And we have something similar for multiplication. So let me write some dots on screen here. And I want you to count how many dots there are on screen. Or tell me how many. You don't have to count them, but tell me how many dots there are. Some of you might say, well, there's 5 groups of 3. Here's a group of 3, and there's 5 of them. So that's 5 groups of 3, or in other words, 5 times 3. And so there's 15 dots on screen. Others of you might look at it a little bit differently. Instead of seeing 5 groups of 3, maybe you see 3 groups of 5. So here's a group of 5, and there's 3 of those, so that's 3 times 5, which still gives us 15 total dots on screen. So again, the important thing here is that 5 times 3 is equal to 3 times 5. And there's nothing special about 5 and 3. This works for any two numbers. So this is the commutative property of multiplication. And we write a times b is equal to b times a. So given any two numbers, you can multiply them in either order you like. These two properties seem simple, the commutative property of addition and the commutative property of multiplication, and they are simple, but they're really important, so they'll be good to know. Okay, see you in the next video. In the last video, we learned how addition and multiplication have this nice property called the commutative property. Now we're going to learn a new property that addition and multiplication both have, and it's the associative property. So addition is associative. Let's start with addition here. So a plus b as a group plus c is the same thing as a plus the group b plus c. So really it tells us something about how we're grouping addition, where we write these parentheses. And really it's saying it doesn't matter where we write them because they're the same. So let's see an example. 9 plus 3 plus 5. And we'll do 9 plus 3 as a group. Well, this is equal to 9 plus the group 5 plus 3, or 3 plus 5. So 9 plus 3 is 12 plus 5. And then on the other side, we're going to get 9 plus 8. 12 plus 5 is 17. 9 plus 8 is 17. And so we can see the associative property in action. Doesn't matter where we put the parentheses, both sides are equal. Since it doesn't matter where we put the parentheses, what we're going to do is just drop them. The parentheses don't tell us anything interesting, so we don't need them. It doesn't matter where we put them, so why put them anywhere? Okay, so that was addition. Multiplication is the same. Multiplication is associative. So we write that as A times B as a group times C is equal to A times the group B times C. So it's the same thing, and let's see an example of this. Five times 3 as a group is equal to 5 times the group 3 times 2. So 5 times 3 is 15 times 2, and then on the other side we'll get 5 times 6, and 15 times 2 is 30, 5 times 6 is 30, so you can see that both sides are equal. If you're wondering if anything isn't associative, in the next video we'll see that subtraction is not associative, and we'll see how that works. Okay, see you then. I want to talk to you about subtraction. Subtraction is kind of nasty. It doesn't have very many good properties that we like. For instance, 6 minus 2 is not equal to 2 minus 6. Why? Because 6 minus 2 is 4, and 2 minus 6 is negative 4. So obviously 4 is not equal to negative 4. So subtraction is not commutative. And the example we just gave is 6 minus 2 is not equal to 2 minus 6. There's other things wrong with subtraction. For instance, subtraction is not associative. So an example of that would be 9 minus 4 grouped minus 1 is not equal to 9 minus parentheses 4 minus 1. And we can go through this just to prove it to ourselves. 9 minus 4 is 5 minus 1. And then on the other side we have 9. Well, 4 minus 1 is 3, so 9 minus 3. Those are not equal because 5 minus 1 is 4, and 9 minus 3 is 6. So subtraction is not associative. And there's another reason subtraction is not that great. But first, let's just write our example down. So our example here was 9 minus 4, parentheses, minus 1, or parentheses 9 minus 4, and parentheses minus 1, is not equal to 9 minus parentheses 4 minus 1. Okay, another reason that subtraction is not that great is because sometimes it can be confusing with the order of operations. So for instance, 10 minus 6 plus 2. Maybe we're not sure, should we do subtraction first or should we do the addition first? So we think of the order of operations, parentheses, exponents, multiplication, division, addition, and subtraction. And that looks like we're supposed to do addition first. Addition comes before subtraction. So this would be 10 minus 8, which would be 2. But that's wrong. That is the wrong answer. What we forgot is that what the order of operations really says is then when you have only subtraction and addition left, do everything from left to right. So this is really 10 minus 6, which is 4, plus 2, which is equal to 6. And that's the right answer. So the third reason subtraction isn't that great is because subtraction can be confusing with the order of operations if we're not careful. And our example for this one is 10 minus 6 plus 2. But all is not lost. There's something we can do. We can actually turn subtraction into addition, because a minus b is an abbreviation for a plus negative b. So let's look at our first example. How would that work? Well, 6 minus 2 is equal to 6 plus negative 2. And now since we're doing addition, we know this is commutative. So we can change the order. So now we have negative 2 plus 6. Notice in this example, the negative sign stays with the 2. In our original example, the negative sign went to the 6. That was the problem. The negative sign was on the wrong number. Okay, so when we think of subtraction as addition of a negative number, we get commutativity back. A little note about the notation here. Why do we put parentheses around the negative sign? It's really because doing it that way is ugly and unclear, and you might even confuse somebody if you're not very neat. So instead what we do is we put parentheses around the negative sign so that everything is really clear. If we look at this, it's very clear what we mean. We mean 6 plus negative 2. And now anybody looking at that will know exactly what you mean. Okay, so that's just a note about why we put parentheses around the negative sign. Let's talk about what happens with associativity when we think of subtraction as addition of a negative number. Well, subtraction really does become associative again because we're turning it into addition. So let's just look at our example here. 9 minus 4, parentheses 9 minus 4 end parentheses, minus 1, is equal to 9 plus negative 4 plus negative 1. And now, this is all addition, and since addition is associative, it doesn't matter where we put the parentheses. We could put them around the 9 plus the negative 4, or we could put them around the negative 4 plus the negative 1. And why don't you try doing that at home? See if you get the same answer. You should, because addition is associative. Okay, and finally, let's look at our third example. Does this fix the problem? So 10 minus 6 plus 2, if we think of this as 10 plus negative 6 plus 2, now if we do the negative 6 plus the 2 first, we would get negative 4 from that. So 10 plus negative 4, which is equal to 6. So even though we did the negative 6 plus the 2 first, we got the right answer. Okay, so the important thing to take away from this video is that subtraction is not commutative and it's not associative, but we can think of subtraction as addition of a negative number, and then we get all those nice properties back. Okay, see you in the next video. Well, let's talk about fractions. What information does a fraction convey? So if I have the fraction 1/4, what type of information does that convey? Well, it conveys two pieces of information. And they relate to, it's always related to one whole thing. So for instance, we have a whole circle here. You can think of this as a pie. It's usually the easiest way to think about it. So we have one whole pie. The bottom number, known as the denominator, so let me write this out. Denominator. The denominator tells us how many pieces to cut this pie into. So in this case, we're going to cut the pie into 4 pieces. Now it's important that you remember that the pieces are equal sized. They're always equally sized pieces. So there we go. We've cut this pie into 4 equally sized pieces. Now the top number, its name is the numerator, and it tells us how many pieces of that pie we have. So in our case, we have 1 of the 4 pieces. Okay, if this 1 was not a 1, but was instead a 2, well then we would have 2 of the 4 pieces. And so on and so forth. If it was a 3, well then quite simply we would have 3 of the 4 pieces. Oops, sorry about that. And if it was a 4, well then we'd have 4 of the 4 pieces, or in other words, we'd have 1 whole pie. Okay. Fair enough. What if we instead had, or well, let's look at another example, I should say. What if we have now 1/3, the fraction 1/3. Well, first of all, how many pieces of pie are we going to have? How many pieces are we going to cut this pie into? We're going to cut it into 3 equally sized pieces. So again, the denominator, the number on the bottom, tells us how many equally sized pieces to cut our pie into. How many pieces, how many of these 3 pieces are we going to have? Well, we're going to have 1 out of the 3. That's what the numerator tells us. And you can do this for any numbers. You could cut a pie, for instance, into 8 pieces. So you could have 5 out of 8 pieces. So this would be a pie cut into 8 equal pieces, and you would have 5 of them. And again, you could do that with any 2 numbers. So the idea behind a fraction is really, really simple. Things get a little bit more involved when we start talking about adding fractions together or multiplying fractions and things like that. So let's go ahead and look at doing things like that in the next few videos. See you then. All right, let's learn how to multiply fractions. It's really the easiest thing you can do with fractions. So what do? All we have to do is multiply the top 2 numbers, so 1 times 3, which is 3, and then divide by the bottom 2, multiplying the bottom 2 numbers, so 4 times 5 is 20. And that's it. You multiply across the top, and then you multiply across the bottom. So if you can multiply numbers, you can multiply fractions. It's just that easy. How about 3/7 times 4/11? Well, hopefully you've already done this in your head by the time I finish writing. 3 times 4, 12. 7 times 11, 77. And that's our answer. Easy as pie. Okay, what happens if we have just a single number times a fraction? So let's do like 5 times 2 over 17. So now we don't have a fraction. We have just a number times a fraction. Well, let me pull you aside for a second and just tell you that 5 is equal to 5 over 1. And if you remember what we talked about, that should make sense. This tells you how many pieces to cut the pie into. Well, if you only cut it into one piece, you haven't really cut it at all. It's just still one whole pie. And you have 5 of them. You have 5 whole things, so you just have the number 5. You have 5. One other way to look at this, in case you're still curious, is this is the same thing as 5 divided by 1, which you should know is simply 5. Okay, so you got that. So coming down here, if we wanted to, we could rewrite this as 5 over 1 times 2 over 17. And now we know how to do this. 5 times 2 is 10, and 1 times 7 is 17. So 5 times 2 is 10, 1 times 7 is 17. So we could write this intermediate step where we write 5 as 5 over 1, but I recommend that you don't even do that. You don't even waste the ink doing that unless it really helps you, because we could easily just know that when we encounter a number times a fraction, what happened here? A number times a fraction, you just always multiply the number to the numerator. For this reason. Okay, that's multiplying fractions. There's really nothing else to say. It's the simplest thing you can do with fractions. See you in the next video. I want to talk to you about simplifying fractions, or what's sometimes called canceling fractions. So let's start with the basics. 5 divided by 5 is what? It's 1, right? Any number divided by itself is just 1. So negative 1,131 divided by itself, again, is just 1. What about fractions? Something like 3/7 divided by 3/7. Well, a fraction is just a number, and so we're dividing it by itself, so we get 1. What about 0? 0 divided by 0. Well, this is not equal to 1. This is the only exception, and it's because we can't divide by 0. If we tried to divide by 0, the universe would split open and your mother would cry. It just would be terrible. So 0 divided by 0 is undefined, and that's the only exception. So we end up with this nice little rule. If a is not equal to 0, then a divided by itself is equal to 1. So what does this have to do with canceling fractions? Well, let's see a really simple example. 2 divided by 4 is the same thing as 2 times 1 divided by 2 times 2. Well, because we know the way fractions multiply, that's the same as 2 over 2 times 1 over 2. But 2 over 2, we just talked about, that's just 1. So we're left with 1 times 1 over 2, or in other words, 1/2. And 1 times anything is just that thing, so we're just left with 1/2. So it took us quite a few steps, but we simplified 2/4 to 1/2. Let's see another example. 6 over 27. Well, 6 is 3 times 2, and 27 is 3 times 9. And again, we can split this up into 2 fractions. So we end up with 3 divided by 3 times 2 divided by 9. The 3 over 3, that just becomes a 1. So we're left with 1 times 2 over 9, which of course is just a 2 over 9. So this is taking a lot of writing. It takes quite a few steps. So maybe we want to abbreviate this. We know how everything's going to work out. We're going to end up multiplying by 1. So instead of writing out those steps, we're going to do something like this. Let's see this again, only with an abbreviation. So 6 over 27 is 3 times 2 over 3 times 9. And we know that 3 is going to cancel to 1, so we'll just cross it out. And that's an abbreviation for those steps underlined in orange. And we end up with 2/9. Okay, so this can actually be really useful. Let's combine simplifying fractions, what we're doing in this video, with some things we've already learned. What if we had something like 3 times 3 over 47 times 2 over 13, 13 times 3 over 47 times 2 over 13 times 47? Well, it looks like the 13 in the denominator there and the 13 on the left maybe will cancel, and the 47 in the denominator and the 47 on the right might cancel. So since multiplication is commutative, something we've already learned, we can rearrange this any way we want. So we'll rearrange it this way. Let's put the 13s together and the 47s together. Also, multiplication is associative, which means we can group it any way we want. So let's not only put them next to each other, but let's actually group them. And now we know the way fractions multiply. That's something we've already learned. 3 times 2 over 13 is just 13 times 2 over 13 is just 13 times 2 over 13. We get something similar over on the right-hand side. And now we can just cancel. But since this is our first example, let's just go through one more step. So 13 times 2 over 13 times 1, right? 13 is the same as 13 times 1. So we'll just put that 1 in there. And 3 times 47 is the same as 47 times 3. And 47 is the same as 47 times 1. And now we're all set to cancel. So we're just left with 2 over 1 times 3 over 1. Well, 2 over 1 is just 2, and 3 over 1 is just 3. So this is 2 times 3, which is equal to 6. And it took us quite a few steps because I wanted to write everything out so we could see how this works. But the main point here is that we can use all of our rules to simplify that multiplication. Okay, what if we have addition instead of multiplication? Can we cancel then? Something like this. Well, the answer is definitely no. Doing something like that is wrong. You don't want to do that. Why not? Well, let's see. If we canceled, we'd be left with 1/3. So instead of canceling, let's see what happens if we just do this addition and try and simplify. So 5 plus 1 is 6, 5 plus 3 is 8, and then we're left with 6 is 2 times 3, 8 is 2 times 4, and now we know those 2's cancel, and we're just left with 3/4. Well, 3/4 certainly is not the same thing as 1/3. If we had canceled the 5's originally, we would have gotten 1/3, but of course 3/4 does not equal 1/3. So that's just an example of why this doesn't work out. It doesn't work out because we need to be multiplying by something over itself. Because when we're multiplying by something over itself, we're really just multiplying by 1. And that's where the simplification comes from. But when we have addition, we don't have any multiplication, so we're certainly not multiplying by 1. Okay, see you in the next video. I think it's pretty clear when we think about it that 1 whole pi is the same thing as having 4 out of 4 pieces of pi. So here's a whole pi. Oops, sorry about that. Fill that in. That's the same thing as having all 4 pieces of this pie. So here's the whole pie. Here's 4 out of 4 pieces of pie. It's the same. You have the same amount of pie. And this would be true no matter what number we chose. So we could have 4 out of 4 pieces. We could have 7 out of 7 pieces of pie. We'd still have the whole thing. We could have 1,001 out of 1,001 pieces of pie. If we have as many pieces as well, let me put it this way. If we cut the pie into 1,001 pieces and then we take all 1,001 of them, well, we have the whole pie. So that works for any number. That works for any number. And we can erase the pi part and just think of these numbers. So 1 is equal to 4 over 4. Just like we were just saying, it's also equal to 1001 divided by 1001, or any number divided by itself. So a number divided by that same number. Okay, knowing that, what happens if we multiply let's say we have 2 over 2 times 1/4. Well, we know how to multiply fractions. That's easy. It's just 2 times 1, which is 2. And then we have 2 times 4, which is 8. So let's see what 2/8 looks like. So here's a pie cut into 8 equal pieces, and we're going to take 2 of them. Now, let me go back and do something here. Oops. There we go. Okay, so all I wanted to do was show us again what 1/4 looks like. So 1/4 is this exact same amount of pi as 2/8. Why is that? Well, because of this right here. We multiplied by 2 over 2, but we just talked about the fact that that's the same thing as 1. This is like all the 2 over 2 is the same thing as 1, so it's like we multiplied by 1. 1 times 1/4 is equal to 1/4. So these two equations are giving us the same information, really. 1/4 and 2/8 are the exact same amount. It's just that we kind of disguised 1, so to speak, by calling it 2 over 2. But we just talked about the fact that that really is the same thing as 1. Make sure you understand this. This is something that will come up throughout your math career, the fact that you can multiply by a number over itself, and that is the same thing as multiplying by 1. Okay, I hope this helps. I'll see you in the next video. All right, here we have a very simple, two very simple fractions that we're adding together. We have 1/4, 1 out of 4 pieces, plus 2/4, 2 out of these 4 equally sized pieces. Well, it seems like when we add them together, we should simply get 3 out of the 4 pieces. 1, 2, 3 out of 4 pieces. And that is exactly right. That's exactly what we get. We get 3/4. That should make sense to you. And notice that when we added the fractions, what happened? Only the numerators added. We did 1 plus 2. And the reason is, just like we said, we're adding 1 out of 4 pieces plus 2 out of 4 pieces. Well, that should give us 3 out of the 4 pieces. Okay, let's just look at another quick example. So let's say we have here 5 out of 12 pieces. And we're adding 3 out of 12 pieces. Well, it seems like if we take 1, 2, 3, 4, 5 of the pieces plus 1, 2, 3, we should just end up with 8 out of the 12 pieces. We should end up with 8 of those 12 pieces. And indeed, that's exactly what happens. When we add them together, we just now have a total of 8 out of the 12 pieces. Now, the thing that's allowing us to add is the fact that we're talking about the same sized pieces. Notice that corresponds to the fact that the denominators are the same. So we had 12 pieces, 5 out of 12, and 3 out of 12. So in other words, we were cutting our whole into 12 pieces each time. So every piece is the same size, so we can add them up no problem. We have 5 out of the 12 plus 3 out of the 12, we get 8 out of the 12. Okay, simple enough. What happens though if we have something a little bit different? What happens if we try and add something like, sorry about that, 1/4 to 1/3? So I'll write that out. 1/4 plus 1/3. Well, visually, it's not too hard to imagine. Oops, sorry again. It's just going to look something like this. That's the total amount we have. But what would that look like as a fraction? Well, it turns out we can't write this as a fraction the way that it is. And that's because these pieces are not the same size. We have 3 different sized pieces, and so this cannot be represented as a fraction. Remember, one of the things that we stressed is that a fraction represents equally sized pieces. So for instance, 4 equally sized pieces. Here we had 3 equally sized pieces. But in this last example, we don't have equally sized pieces, so we can't write it as a fraction. So what can we do? Well, maybe we can cut our pie into smaller pieces so that they're all the same size. And we can do that using multiplication. So I'm just going to do something. I know you'll probably have questions about it. How did I know to do this? Or, what's the technique? We'll talk about that in the future, but just follow along for a minute. Let's say I multiply this by 3/3. And let me make some room for myself here. I'm just going to bring that up a little bit. Well, we know how to do that multiplication. It's just going to be 3 times 1 is 3, and 3 times 4 is 12. So this is, shoot, I really want this to be smaller so I have more room. I apologize. So we have 3/3 times 1/4. 3 times 1 is 3. 3 times 4 is 12. Now, we already talked about in a previous video, when we multiply by a number over itself, that's the same thing as multiplying by 1, so it doesn't change the fraction. And you can see that 3/12 is the same as 1/4. It's the exact same amount. Here we have 3 out of 12 pieces. Here we have 1 out of 4 pieces, but we're still talking about the same amount of pie, or the same amount of the whole. It's just there's smaller pieces and we have more of them. Okay, Same thing for 1/3. I want to do something similar. What I want to do is I want to do 1/3 times by 4 over 4. And now we have 4 times 1, that's 4. And 3 times 4, that's 12. And you can see that 4/12 is the same as 1/3. Let me show you. Here, now we have 4 of the 12 pieces, but that's the same amount as 1/3. They're smaller pieces, but we have more of them. Well, hey, look it, what happened now? Now we have 3 out of 12 equally sized pieces, plus 4 out of 12 equally sized pieces. This should end up being 7 out of 12 equally sized pieces. And you can see that here. If you count these up, there's going to be 7 out of the 12 pieces. Now this is the idea behind finding a common denominator. So notice our denominator ended up being the same, a 12 and a 12. And we needed to do that in order to add. Before we did that, we had something like this. We had 1/4 plus 1/3. We couldn't add those. Then we found this common denominator. In other words, we split the pie into the same number of pieces, and then we could add them. Okay, so this is the concept behind finding a common denominator. We will talk about the techniques of finding a common denominator in the next few videos. See you then. Okay, here we want to add 2/5 plus 1/6, and we've already talked about why you need a common denominator in order to add. Now we're going to talk about how do we get a common denominator. One way is to find a least common multiple of 5 and 6, or I should say the least common multiple of 5 and 6. So what does that mean, and how do we do that? Well, what we're going to do is make a list of multiples of 5 and multiples of 6. So 5 times 1, that's 5. 5 times 2 is 10, times 3 is 15, times 4 is 20, times 5 is 25, times 6 is 30, times 7 is 35, times 8 is 40, and maybe I'll stop there. So these are the first 8 multiples of 5. Now we'll do some multiples of 6. 6 times 1 is 6, times 2 is 12, times 3 is 18, times 4 is 24, times 5 is 30. And hey, we can stop because now we have a common multiple, meaning these multiples are the same. And not only that, but this is the least common multiple, because if we look at this list, it's the smallest number that's the same in both lists. In fact, right now it's the only number that's the same. Okay, so that means we want our denominator to be 30. So what we've done so far is we looked for an LCD, a least common multiple, or LCM, a least common multiple, and that's going to be our new denominator. So we want 30 to be our new denominator. Denominator. Okay, well over here we did 5 times what? Well, it was 5 times 6 was equal to 30. Here, it was what? It was 6 times 5, the same two numbers. Okay, how does that relate to our original problem? Well, that means to get the denominator to be 30, we need to multiply by 6. 6 times 5, that was Okay, let's try and add these two fractions together by finding a common denominator. And the way that we're going to find a common denominator is by finding a least common multiple between the two denominators we're given. So we have 25 and 15. We want to find a least common multiple. So multiples of 25. 25 times 1 is 25. 25 times 2 is 50. Times 3 is 75. Times 4 is 100. Times 5 is 125. Times 6 is 150. Times 7 is 175. And I'll stop there. So we got 7 multiples. Now let's do 15. Times 1 is 15. Times 2 is 30. Times 3 is 45. Times 4 is 60. Times 5 is 75. And now we can stop because we notice that there's a 75 in both lists. And so 75 is a common multiple. It's also the least common multiple because it's the smallest number that's the same in both lists. Okay, so now it's time to figure out how did we get 75? Well, we did 3 times 25 was equal to 75. And over here, we did, this is equal to 5 times 15. Okay, so we know what we need to do now. We're going to multiply this by 3 over 3 because we want this denominator to be 75. But we don't want to change the fraction, so we have to multiply by 3 over 3 because that's the same as multiplying by 1. So we don't change the fraction. We're just changing the way it looks. Okay, over here we need to multiply by 5 over 5 because again we want this denominator to be 75 and 15 times 5 is 75. Okay, let me get rid of that. And what's our result? Well, 4 times 12, 3 times 4 is 12. 3 times 25 is 75 like we said, plus 7 times 5 is 35. And 15 times 5 is again 75, just like we said. And now we have a common denominator. And so we can add these two fractions together. So this is going to be 12 plus 35, which is 47. And we just keep that same common denominator, 75.